So my name is Martin Schubert. I'm a virtual reality designer at Leap Motion. That is my job title. I was a developer evangelist when I first came there. Now my title is virtual reality designer. I'm on Twitter as Mr. Schubert. And if you want to chat about anything that I covered today, just mention me on Twitter and use the hashtag UXVR. So today I'm going to be talking about designing for hands, not controllers. But first I want to give you a quick background on Leap Motion and what we do, and then a little bit about myself too. So, Leap Motion was founded in 2010, and our mission is to break down the barrier between people and technology. And usually that's called the interface. And so the way that we're doing that is by tracking human hands with incredibly high accuracy at really low latency. And so we've been doing that for a long time, for the last 7 years. The way most people have heard about Leap Motion is from our first product, which we launched in 2013. So we launched the Leap Motion controller, which is this little device that you sit on your desk and you plug it in via USB, and you can hold your hands over it, and it recognizes your hands and tracks their movements, and you can see those movements on screen. And so there were a bunch of app developers who made apps for desktop. We sold over 500,000 of them. But then in 2014, with VR having its resurgence, we sort of pivoted a little bit as a company, and we let all of these people who had these devices, over 500,000 of them, mount them onto the front of a VR headset. At the time it was a DK2, now you can mount them to the front of a Rift or a Vive. And for the first time you could put on a headset, and this is before Oculus Touch came out and before the HTC Vive controllers were out. So really it was the first 6 degree of freedom input. So you could put on a headset, put this little device on the front, look at your hands and they were tracked, and you could use them to interact with virtual objects. In the meantime, in the last couple of years, we've focused even tighter on mobile virtual reality and augmented reality, which is all going to be mobile, specifically because input on those platforms right now is pretty terrible. Nick had a great presentation there, and the lowest common denominator is a laser pointer on your face, which kind of sucks. So as a company, we're really focused on being embedded in future headsets that come out. So we've been working really hard on a new sensor, which you can see kind of sandwiched in between that exploded axon diagram there, that's even thinner, even smaller. It's about the width of a pencil. And it has a wider field of view, so instead of being 135 degrees, it's 180 degrees by 180 degrees. So what we're focused on right now is the hardware and also getting the software to run on a phone processor and draw less power and all the things that come with mobile. So for us on the horizon in 2018, hopefully you'll start seeing mobile headsets that have like Leap Motion, powered by Leap Motion or something on them. And instead of buying an accessory that you put onto a headset, it'll just be a part of the headset. And really soon people will be like, how did we not have hands in virtual reality? So similarly, I did not start out in virtual reality. I actually graduated in 2013 from the University of Southern California with a degree in architecture. And there's actually one of my friends who graduated with me from architecture is here right now, switching from architecture to VR as well. And yeah, get out of architecture. VR is the future. And so once I graduated, I did 5-year pre-professional degree, but I didn't want to become a professional architect. I wanted to look at other creative industries. So for a couple of years, I was at an advertising agency called 72 and Sunny in LA. I was working on the Samsung account and the Google account. And that was right around the time of the Oculus Kickstarter. So I was really hyped about that. The Matrix is my favorite movie, and so I was like, wait, this is a real thing. I got the agency to buy a DK1 and tried to integrate it into campaigns, but at the time, even now, a lot of agencies think VR is a gimmick, and so it was kind of a hard sell. But I started learning Unity from YouTube tutorials and making projects in evenings and weekends. Then in 2014, when Leap was making their shift from desktop to VR, they ran a competition, a 6-week game jam, for people to make content that used Leap as an input for a VR experience. So I made this experience called Weightless, which is basically a space station simulator. You're floating in a space station above Earth, and there's objects that are floating around in zero gravity, and you can boop them around. And that ended up coming second in the competition. So I started talking to Leap about how I could work with them, and joined the company in 2015, and I've been there for the last 2 years as a designer and developer. So what I want to talk to you guys today about, there's 4 sections, and they go from sort of really high level, industry medium level, to really granular examples of actual interactions that I'm working on day to day. So we're going to go from sort of the paradigm level of like all of this technology, to the input level, to the interaction level, and then we're going to go down to nitty-gritty of actual examples of things you do with hands in VR. So the first topic is computing is becoming spatial. And to me, this is really the most exciting thing about all of the stuff that's happening right now, especially with my architecture background. So there are a lot of terms that people use for the things that we're seeing today. This is a continuum from Paul Milgram called the reality-virtuality continuum. On the left, there's the real world, and on the right, there's a fully virtual environment. And so like virtual reality, augmented reality, cinematic reality, mixed reality, immersive computing, all these terms can kind of fit along this spectrum. But for me, it's actually more helpful to think about the progression of technology as a whole rather than just sort of what's happening right now. So if we look at computers when they first came about, there were these massive mainframes, right? So in order to interact with them, you had to learn the completely abstract language of punch cards and then feed those into the machine. It took specialized training, and only very few people actually did this. Then the first transformation happened with the direct text interface, where a keyboard let people push buttons which corresponded to letters, so you could type words, and the computer would recognize the words and then execute commands. So that's a huge jump in usability and accessibility. The next transformation happened with the graphical user interface. So now we're using images, and we're using icons, and we're using a mouse in 2 dimensions to click on things, and that brings in the paradigm of windows, icons, menus, and pointers, and the analogy of a desktop to organize information, which we're still pretty much using today. Then the next transformation came about around 2007 with the iPhone and the touch screen and touch input, which let us interact with digital objects directly for the first time without using a proxy of another instrument to do so. So when you look at it like this, from what computers started as to the progression that they've been moving along, it makes a lot more sense when you place all of these other technologies that we're seeing today. And when you look at this in context, I actually find it easier to group these new technologies by what separates them from what came before. And to me, the biggest difference between what we're seeing today and what has come before is that for the first time, computers are letting us interact with them spatially. When we use these technologies, we're not looking at a screen anymore. We're inside a space. And so my favorite term for all of these technologies is actually spatial computing. And so with each previous transformation, as the output transforms from screens that we carry around in our pockets to devices that we wear on our heads that give us the illusion that we're in another space, I think that the input is also going to transform. So the same way that the keyboard was to text input, and the mouse was to windows, icons, menus, and pointers, and our fingers are to the little screens in our pockets, I think that our bodies are to the space around us. They are the interface that we use to operate in a 3-dimensional world. So I think that they'll be the interface that we use to operate in a spatial computing world. So to sum up this first section, I think spatial computing uses the space around us as a medium to interact with technology. And space is the native medium of human interaction. We're 3-dimensional creatures living in a 3-dimensional world. And over millions of years, we've evolved to engage spatially with the world around us. So I think this is a pretty exciting thing. It feels like technology has sort of finally caught up to what evolution has built us to be able to do. So that brings me to the next section, which is that controllers are not hands. Seems kind of obvious, but at the end of this, I hope that you all really, really agree with me. So virtual reality controllers, Nick gave a great intro to those. So I don't really have to explain 3 degrees of freedom versus 6 degrees of freedom. I kind of think 3 degrees of freedom controllers will go away pretty soon once we figure out how to do 6DoF in a way that's scalable. But even 6DoF controllers are still very much controllers. So this diagram up here, without the missing part of it, the Xbox controller on the right, and then all of the buttons that exist on the Vive controllers and the touch controllers, you can see that they were designed very much for gamers. They offer spatial tracking, yes, but they are still very much game controllers. And if you were to hand one of these controllers to someone who has never played a game before, they would probably be overwhelmed, especially so if they're wearing a headset that doesn't let them see their fingers, and so they're fumbling blindly to remember what you told them the buttons were. You'll find also that the most accessible games and some of the most successful ones actually don't even use all these buttons. Job Simulator, for instance, you press one button to close your hand and pick things up, and that's pretty much all you use. Tilt Brush, most of the time people just paint with one brush stroke until you give them the palette and explain a whole bunch of other things. So really, these actually just get demoted down to one button inputs. There's also been a lot of talk about enabling hand presence through controllers. And I think hand presence, maybe it's an old term. I kind of feel like Oculus coined it to promote the touch controllers. But looking at this animation from Oculus's website, which is overly generous and kind of misleading, you can see that even with their marketing, there are parts where the virtual hand and the real hand just don't match up. See if you can catch it at the end here. They try to sneak it in. Like, what? And they also turn the controller sideways to do it, and they cut it at the end of the GIF, which I'm like, that's a little sketchy. But so in this example, like, there's no real way that you can do that with the controller. They have capacitive touch sensors on the controllers, meaning that you can press the button and they know if you're pressing it or not. But because it's capacitive, they can also tell if you're touching it or not. So you can let go of the controller and then your finger will extend. But there's only 2 of those, so you can't really do that open hand action. Really what's happening is the virtual hand is a preset, I call them doll hands, preset hand that has a couple of animations, and depending on how far your fingers are, it blends between those animations. And at the moment, all this stuff is really new, so unless you're working with hand tracking every day, you probably don't notice it, although subconsciously you definitely do. But having your hand not do what your actual hand is doing makes these representations feel really static and lifeless, and you don't get the feeling that your body is actually in virtual reality with you. So again, in this example from Job Simulator, those hands, they use gloves, which is another like kind of look towards that they know that they're not real hands. In Job Simulator, when you grab an object, your hand actually disappears because they don't want to show your hand doing the wrong thing. Also, they have a cartoony aesthetic, so it works for them. But again, this is reducing your hand basically to a one-button binary, am I grabbing or not? Is it a glove or is it an object? So these controllers that Valve has shown off, the Knuckles prototype controllers, are actually super interesting. I'm really excited to try them. Basically, the idea is that the controller straps into your hand, and so you can hold it, but also if you let go of it, if you open your hand completely, it's strapped into your hand so you don't drop it. And they have capacitive sensors on the fingers. And so on the right, you can see some test footage from how that looks in-game. And that's a big step towards having your hands actually in the game, but it is still a more advanced version of doll hands. You've got a set animation and you're blending between different poses depending on a single scalar factor of how far your hand is from the button. I am really excited to try those though. Also with the Knuckles controllers, this isn't really a solution for mobile VR or for AR, because even with these controllers, you still need external lighthouses to track the controllers, and they're pretty bulky things, so you're not going to carry them around with you if you're on the move. So basically, 6 degree of freedom controllers are one spatially tracked point plus a bunch of modifiers, buttons, touchpads, joystick, capacitive sensors. Still, they're one point in space, reducing your hand to one point in space. At Leap, we track your hands at the moment as 26 spatially tracked points. So we're actually tracking every joint in your finger and making up a whole hand skeleton. And I think this diagram is probably the clearest way I can make this point. If you strip away all of the graphics and the doll hands and the animations and just look at what parts of your body are actually being tracked in virtual space, on the left you can see that the head is being tracked, we know where the headset is, and then the controllers are these rigid things and we know where they are in space. So you're basically 3 points, that's what you exist as in virtual space. On the right you can see, well, he just looks much more like a human being. So what you're seeing here is the raw feed from the Leap Motion sensor. So the way the sensor works is it shines out infrared to illuminate your hands, and then it has infrared cameras that film your hands, and then we do a bunch of crazy computer vision to figure out where your hands are and what their position is. So what you're seeing is the raw infrared black and white video, and then those dots are the joints that are being tracked as I move my hands around. And as I said before, I think spatial computing's unique strengths lie in its ability to let us use the space around us as a medium to interact with technology. So I might be coining a term here, probably not, but I think that the more spatially tracked points you have, the greater your spatial agency. And I think that spatial agency, having a greater spatial agency, allows you to improve many different aspects of being in a virtual space and the experience that you get from these technologies. So I want to talk a bit about the demo that I was showing yesterday and the day before that I think some of you guys, hands up who tried the demo that I was showing yesterday and the day before. All right, cool. Half of you guys. So I've got a video of it so you understand what I'm talking about. So to demonstrate the advantages of this concept of spatial agency, my colleague Barrett and I, Barrett's in the front row over there. There he is. We created an experiment called mirrors. And so mirrors are this really powerful thing in virtual reality because they help you to link your body representation with yourself. And I think that's because in our everyday lives, except for photos and videos, mirrors are really how we see ourselves most of the time. So if we see ourselves in a reflection and we move and the reflection moves, we identify with that image and we think, that's us. So we wanted to demonstrate how spatial agency increases two things: body presence and expressive movement. Let's see if this will play. It will. I'm not sure about sound, so I'm going to turn it kind of down. So body presence. Body presence, it's also called the illusion of virtual body ownership or avatar embodiment. Basically, it's the idea of how much do you feel like the body that you see in virtual space belongs to you. So Leap brings more of your body into virtual space than any other input. So Barrett created this rig, this upper body avatar rig. And basically, it's driven, we know where your head is and we know where your hands are. And through some nice animation, Barrett knows where your elbows and your shoulders should be. So when you look in the mirror, you actually see a full upper body. And when you move your arms, the elbows and the shoulders move. And it really convinces you that you have become this cloud of particles. The other thing is the representation of yourself is made up of all these little particles. And each particle, its properties are driven by the speed of your movements. So in this first example, if you don't move much, it's kind of like dark and blue, and the faster you move, the more it color shifts through to red. In this example, like if you don't move much, you're pretty much invisible, and then the more you move, a bunch of stuff flies off your fingers. So what we wanted to do was, one, make you really feel like your body was in there with you, and that your body was this crazy particle cloud, and also to emphasize how expressive you can be when you aren't just these stub doll hands, but you're actually a dexterous human with fingers and joints. And some people dance, some people just wave their hands, but you guys, half of you have tried it. So music does make it better, but you guys get the gist. You're also made of fire. There's a couple other ones in there. Yeah, we did some fun mixed reality compositing tricks. So this isn't actually AR, but all right, that's enough of that. Maybe. Nope, I gotta click away. All right, this was in case the video didn't work, so we'll skip through these. Okay, so we've got your hands in VR, and we know that your hands aren't controllers. So now the question is, what are we gonna do with them? So let's get down to the actual details of designing interactions for hands in virtual reality. So science fiction over the years, especially movies like Minority Report, which I've heard about every week for the last 2 years, have led many people and designers and developers to think that three-dimensional gestures are the future of interacting. And over the years of working with them, we found that there's actually a couple of issues. When they work, they feel really great. They make you feel like you have magic powers or superpowers. But as an example, real quick, if everybody could just hold up your hand and then just do a circle gesture for me. Everybody do a circle gesture. All right. You all did it differently. Everybody did it differently. Some of you guys went like this, some of you guys went like this, some of you guys went anti-clockwise, maybe you went down here. So when I say to do a gesture, or when I communicate it either in text, verbally, even if I showed you how to do it, you'd all probably do it slightly differently. One finger, multiple fingers. So gestures, everybody does them differently. They're difficult to teach people because of that. They're also really hard to define a start and an end. If you had to actually analyze, all right, you start here. What if you start down here? How many fingers? Also, because of that, because it's hard to define a start or an end, people accidentally trigger them all the time. Like you could be putting your hand down and accidentally do a down swipe. abstract, contextless gestures are really difficult to code for and really difficult to teach users. And also, the more of them you have, unless they're really metaphorical, so if you wanted to raise something, you did this. If you wanted to save a file and you had to do a circle gesture, the more of those you have to remember, the more of a cognitive load you're putting on the user. So if we're not going to use gestures, then what are we going to use? Well, if you remember earlier, I described that we're not tracking your hand in its general location. We're tracking it as a full skeleton, which actually means that you can use your hands pretty similarly to how you use them in the real world to manipulate physical objects. If you want to pick up a block, I don't think you should be pressing A, or I don't think you should be doing a circle gesture. I think you should reach out and you should pick up a block. Doing it this way taps into a lifetime of experience using your hands to do physical manipulations and also millions of years of biology. It also removes the abstraction, so there's a minimal learning curve when you pick up a block how you would pick up a block. It also takes advantage of VR and AR's strengths with depth and volume and parallax, being able to tell the distance between objects really easily. And a nice extra is that field of view is less of an issue when you're doing circle gestures or something, as opposed to if you want to pick up a block. Normally you look at the things that you want to interact with. However, interacting with virtual objects using your bare hands is not a simple thing. Game physics were not designed for human hands. Physics engines in game engines really, and I'm grossly oversimplifying, have one job, which is when objects overlap, physics engines push those objects apart until they're not overlapping anymore. That's a problem when your hands are in the real world and nothing is stopping them. So when you go to grab a block, like in that top example, your fingers don't stop at the edge of the block. They'll go through the block. And the frame that your fingers go through the block, the physics engine just goes, okay, well, I have to move that block. And so every time you try to grab the block, it just scoots out of your hand. Similarly, with the second example, if you push down on a stack of objects into the floor, the blocks have nowhere to go, so they just shoot out the sides. So at Leap, we had to build our own physics system, which sits on top of the existing physics in Unity called PhysX. And our system is called the interaction engine. And it handles grabbing and releasing and something called soft contact, which lets you have these subtle interactions like rolling your hand over a block. It lets you, when you're pushing objects into some sort of impossible configuration, your hands phase through them, but then if you wanted to scoop them up through the floor, it lets you do that. It's this really incredibly complex system that we just released out of beta that anybody can download from our website and just put into Unity, and then all of a sudden you have these interactions at your disposal. So we're doing all this sort of hard foundational work so that you guys don't have to reinvent how to grab a block and you can just jump to making your content. So, as we're talking about content, down to the last section, this is about notes from actual interactions that myself and Barrett are working on day to day. So, this is a control panel from the Rick and Morty VR game. And it's a typical example of what I call arm-scale user interfaces. So these controls have all these affordances on them, like handles and levers and dials. But when you interact with them, you aren't grabbing the handle or the lever or the dial. What's really happening is, although your doll hand looks kind of like it's doing it, actually it disappears because it's made by Alchemy Labs as well. You put your controller in this large invisible trigger volume, then you pull the trigger on the controller, and then you move your whole arm. Or with those buttons, you put your whole hand on a button. And these are macro level sort of arm scale movements where you have to pivot at your shoulder or at your elbow. But using the interaction engine as a base, we can create these finger scale user interfaces that are much closer to the ones that you're used to when you are interacting with things in the real world, like a keyboard or a touchscreen. And so this diagram, again, you can see that there's sort of a higher level of interaction resolution when you're using your fingers to press buttons as opposed to your whole hand. And so an experience that Barrett and I have been working on, it's called a sculpture demo at the moment. It's basically a demo where you have a sculpture in the middle and a whole bunch of control panels around you that let you tweak variables of the sculpture. So when I was looking at making this control panel, the first thing I looked at was how can I make components that exist in 2 dimensions, like buttons and sliders, more interesting in 3 dimensions and maybe give the user a little bit more feedback than they would normally get. So in this example, you've got buttons, and although the GIF is really choppy, when you get close to them with your finger, there's a ring that slides up on the outside that shows you how close you are basically to pressing the button. And once you get close to touching the surface, the ring is right at the edge. Similarly, there's one with sliders. We can kind of see that as you get closer, there's a ring that expands. And so you know just how close you are, and then you can slide it across. After that, I wanted to look at trying to bring other 2D interaction paradigms into 3D. So dragging and dropping is, I think, one of the most direct metaphorical interactions that you can do on a 2D screen. So I wanted to see how that would look at 3 frames a minute in 3D. So in this example, in order to change the mesh that makes up the sculpture, which is slightly off to the right of the screen, you grab an object and then place it on a podium. And similarly, there's a bunch of little animations happening where as you get closer to objects, they become more of a wireframe, so you can grab them, things highlight. I mean, it's the same thing you would be doing in 2D user interface design, but expanded for 3D. And then after that, I was curious to explore if recreating a physical input in virtual space would be compelling. So physical trackballs are this highly tactile input with a whole wide spectrum of interaction possibilities. You can dial them with a finger, you can spin them with your whole hand. So I wanted to see if they would be similarly compelling in VR. And turns out they are pretty fun to play with and spin. And then lastly, color pickers. So using a color picker in 2D, normally you've got like one color, you've got hue, saturation, lightness or something. So I wanted to see if in 3D we could do something that was a bit more fun, that felt a bit more like exploring color space. So this is a 3D color picker where the XYZ coordinates of each of those cubes determines its RGB value. And there's 3 colors that you can change in the demo. So you can grab these cubes and push them around and slide them around. And it feels a lot more like you're exploring color space rather than directly inputting RGB values. And so this GIF, which really is not playing well, this is sort of how all of these pieces fit together. You've got the sculpture in the middle there, you've got sliders and buttons on the right, you've got 3D drag and drop, and an RGB 3D color picker on the left. And then the last example I'm going to go through is, so when designing interactions for human hands in virtual spaces, it's a really new field, and it often feels like there's way too much to explore for a little company like us. So Barrett and I have started these interaction sprints lately, where we focus on one piece of the UX of using hands in VR and try to improve it with a couple of different diverse solutions. So for the first one, what we looked at was hand contact effects. So like I said before, your real hands, there's nothing to stop them in the real world. So when you put your hands through a virtual surface, it results in this clipping where the geometry of the static object clips your hand. And it just kind of doesn't look like it should be happening. So we wanted to see if we could resolve that in some way. So the first thing that we did was we added a shader where it checks for intersections and then draws a highlight line around that, and then also shows a little bit of whatever you're putting through the object. And just having that little acknowledgement of your hand going through something really makes it feel a lot more responsive. It makes it feel like the system knows that your hand still exists rather than your hand is just clipping through objects. And when you look at them side by side at 1 frame an hour, you can see that, yeah, it just looks better. It looks more coherent. For the next execution, we looked at when you're pressing buttons, even though the buttons can physically depress in Z space, when they end their travel distance, your fingers normally keep going a little bit, so they still clip through a little bit. So we thought, what about making the fingertips change colors so that when you approach a button, the fingertips gradient towards that color. That one helps you know how far away you are from a UI object, and also when you do clip through, the object and your finger will be the same color, so the discrepancy won't be as weird. We tried it with some objects too. So when you hover over objects, they change the fingertip color. And also we added the intersection effect when you grab them. And so that combination, I think, worked out pretty well. And then lastly, with the interaction engine, grabbing objects and being able to phase your hand through them is sort of a built-in part, is that your hands are going to clip through objects. So one way of resolving this that I thought about earlier was looking at industrial design there's this concept of affordances, which is the idea that the shape of an object can communicate to someone what actions can be taken upon it. So like a bowling ball, for instance, has holes, and that affords the action of putting your hands or fingers into the holes to pick it up. So I thought, well, if you modeled affordances into these objects, maybe people would grab them nicely, and it would not look so weird. Turns out, no, people just grab objects really weirdly, and their hands still clip through them. So static affordances didn't really work out. So we thought, what about, instead of static affordances, we made reactive affordances that moved and dynamically shifted based on however someone grabbed an object. And so in this example, we're raycasting through the fingertips and then driving a dimple that changes shape depending on how far inside your fingers are. This next example, this one's one where you can throw it. This doesn't look that great. We tried also having a fingertip gradient driven by, instead of proximity, depth inside the object. And I think that one works pretty well. And then the very last one, probably my favorite one, is we tried doing an Acme hole style execution, where as you approach an object, it actually spawns a hole, and then you put your finger inside it, and through some shader stencil magic, it makes it look as though your finger actually goes inside without altering the object. And I like this one because it's just, to me, like a good mix of physically plausible in a way, but also magic in a way that can only exist in virtual spaces. And that brings me to the end. So we covered a lot, from the very wide level industry stuff to input to interactions and then to actual examples. I hopefully have convinced you that computing is becoming spatial and that controllers are not hands. Again, tweet at me, use the hashtag, and thanks for listening. And questions if we have time. Just, okay. Well, I'm not going to choose it. Oh, you guys just give someone a mic. There we go.
Hi, fantastic presentation. So for people who are designing and developing in the contemporary VR world where controllers are prevalent, I'm wondering if there's a tool set that you recommend, hardware and software, and also the transition from the controller-based to the hand-based. How do you recommend that we work with that?
That's a really great question, yeah. So at the moment, since we're not in headsets yet, people are using controllers. One quick thing to plug Leap again, the interaction engine system that I mentioned has support for controllers. So instead of using fingers, you can use controllers to hit buttons and pick things up. Totally works. There's a toolkit called VRTK, VR Toolkit, which, if you haven't heard of, is a, I think, open source, community-sourced collection of scripts and locomotion and object interaction, a bunch of other stuff that anybody can download and just bring into Unity. And every basic interaction that you could think of is already implemented with a bunch of documentation and tutorials. So that system is what I'd recommend. And then, did you ask about hardware? Well, yeah. Toolset. So VRTK for VR interactions. Another one that I'll mention that I use a lot, if you are from a design background and coding seems like scary, which it does to me still, there's an asset for Unity called Playmaker that's like $45 on the asset store, and it's a visual scripting tool. It's more like a state machine, but it lets you do basically, like, if the light is off, the light is on, and then have an event that connects them, and it's a visual way of doing scripting. And for me, that was so much more helpful than trying to learn the abstract syntax of coding. So VRTK and Playmaker, and Unity's free, so, and YouTube tutorials are free, so you've pretty much got everything you need. Cool, okay, thanks.